Hi and welcome back to CS33. This is part of Module 8 and this is our first example for the dynamic programming. Aside from the simple example for computing the nth Fibonacci number. So for this video, we will be discussing about how to compute for the coefficients of a binomial expansion. So I am showing here a formula stating the binomial theorem. This binomial theorem is just an equation to specify how you will be able to expand this expression. So using algebra, of course, you can just multiply x plus y n times, but using the binomial theorem, you just need to use this formula so that you can have a summation of terms, and that will be your binomial expansion. And the problem that we will be solving is, given an integer n, output the n plus 1 coefficients. And the n plus 1 coefficients are this number. So that's the n taken 0, n taken 1, etc. up to n taken n. So this is the combination formula. And as we all know, this is equivalent to this one. So this is also read as n choose k or n taken k. Okay, so basically this is the total number of ways how to select k items from a collection or a group of size n. So if we will expand this binomial theorem, we can get something like this. So this one is the left side of the equation, and on the right side of the equation, we have the summation expanded na lang to the coefficient and then the term and so on. Okay, so solving the binomial coefficients is equivalent to enumerating all the combinations from n choose 0 to n choose n. Okay, so luckily, aside from the fact that we know this, we can actually have a recurrence relation, okay, relating the bigger instance and the smaller instances. And of course, we have the base case. To compute for n choose k, we just need to get the sum of n minus 1 choose k and n minus 1 choose k minus 1. Bakit kaya ganito yung recurrence formula? If I chose the first element, I will have to choose k minus 1 out of the n minus 1 remaining. And then, for this case naman, I didn't choose the first element. So, I will have to choose k out of the remaining n minus 1. So, that's the reason why this is how it's computed. So remember that in the dynamic programming approach, there is an overlapping subproblems. And for this one, for computing this one and for computing this one, we can enumerate that there are subproblems that are repeated. So we can use the dynamic programming approach because of the existence of an overlapping problems. The second property is the optimal substructure, and since this is the definition of CFNK, if we get this optimally or exactly and this exactly, we can use it to solve this one. Since we have a recurrence formula that explains how we can get this from this and this, and the idea of dynamic programming is to create a table or a container for the optimal solution, all subset of instances, we can simply enumerate the two parameters n and parameters k. So for the base cases, regardless of the value of n, we have k equal to 0, then we have 1. And then for c, n and n, we have 1 in the diagonal. And then for the remaining parts of this table, we can simply use the general case. So let's start with something that will fill this up. So for this item, suppose our n and k is 2, 1. Okay, so we have 2, 1. Okay, so we need to get the sum of the element na nasa taas and element na nasa katabi ng nasa taas. So this one is equivalent to 1 plus 1. So we can put 2 here. And then you can fill up the table by following this structure. Okay, so let's try to look at an example for n equal to 2. Of course, we can do this by just multiplying the x plus y times x plus y. So we can do that, but we can also try to enumerate based from the binomial expansion. So we have to identify the coefficients, 2 taken 0, 2 taken 2, and then 2 taken 1. Since these are the base cases, we know that this is 1, and then this is equal to 1 plus 1. So the coefficients are 1, 2, and 1. The dynamic programming way how to do it is to create this table, okay, and compute the values for this one first because these are the base cases, and then since n is equal to 2, then 2 taken 1 is 2 because based from this recursive formula, we have this value plus this value. Okay, let's move on to the second example where we have n is equal to 3. So, relatively mas mahirap na yung case na to because magmumultiply ka ulit ng x plus y doon sa expression mo dito. And mas matagal yon if we will compute it. But to get the binomial expansion, so we just need to enumerate this one. So the coefficient for the first term is 3 taken 0. Okay, and this is the base case. This is 1 and 1. And then you simply check out the previous example. So, nandito na tayo sa step na to. To get the binomial formula for n is equal to 3, we just need to compute the contents of the matrix. I just removed the n equal to 0 here, but start with the base cases. So you have to put 1 for k is equal to 0 and put 1 for the diagonal. Ito yung diagonal because you have 1 here kapag meron dito si 0. Okay, so this is for the case where we have n is equal to 2. This number is obtained by getting the sum of this and this, which is equivalent to n minus 1 k and n minus 1 taken k minus 1. To get the value of this one, which is 3 taken 1, you need to get the sum of 2 taken 1 plus 2 taken 0. So that's 3, 1 plus 2. And then to get the 3 taken 2, you need to get the sum of 2 taken 2 plus 2 taken 1. So that's 3. Okay? So this is the coefficients of your binomial expansion. Diba? So, madali lang siya. As you increase this n, the manner of expansion is doing it line by line. And in fact, this may be familiar to some of you. This one, the lower triangular matrix, is actually the Pascal's triangle. And the Pascal's triangle is obtained by getting the sum of the two numbers on top. So, start with 1. So, this is equivalent actually to the k is equal to 0. This is equivalent to n taken n, which is just 1. And then, you get this number by getting the sum of 1 plus 1. You get this number by taking the sum of 1 plus 2, 2 plus 1. So, this is 1 plus 3. So, you can create a larger Pascal triangle by doing it row by row. Okay, so this is the pseudocode for computing the coefficients of the binomial expansion. So look at the pseudocode. It's not a recursive algorithm. For this approach, we are using the bottom-up approach in the computation because we started with the base cases and then nag-increase tayo ng n. In here, we simply create an iterative algorithm that computes for the content of this matrix. Okay? And then, after computing the content of the matrix, pagka nakaabot na siya sa n, then return the row. The previous problem is for computing all the coefficients, but for this pseudocode, it obtains the solution for the n choose k. So, it's the combination formula. But we are using dynamic programming. So the running time of this algorithm is the running time necessary for computing the contents of the matrix. So since this matrix is n by k, so we have a total running time of theta nk. And the space efficiency is also theta nk because you are populating the content of the whole matrix. So that's it for this example. Let's move on to our next example, which is getting the longest common subsequence.